This is Justin Bader, here to teach you Organic Chemistry 1 based on MIT's curriculum for 512. This is video 2 covering material for exam 1. The topics in this video include stereogenic centers and chirality, enantiomers and diastereomers, chair conformations, and Newman projections. Stereogenic centers are an atom, almost always carbon, with 4 different side groups attached. It allows for the R or S configuration around the stereogenic center. On the molecule on the left, the stereogenic center would be the carbon because there are 4 different groups attached. Hydrogen, OH, the methyl group, and the ethyl group. On the molecule on the right, stereogenic center would be at this carbon, and I'll let you convince yourself that there are 4 different groups attached to that carbon as well. Determining stereochemistry. First thing you do is you put the smallest group, usually hydrogen, in the back. Then you number the other groups from largest to smallest, going 1 atom at a time. Then you decide whether it's going clockwise or counterclockwise. In the first molecule on the left, you'll see the hydrogen is already going back into the page. So now we can move on. Out of the 3 groups remaining, the largest atom would be the oxygen. Therefore, this is going to be the largest group. We're going to call that a 1. Then we look at the next 2 atoms attached. They are both carbons. Therefore, it's a tie. So we have to move on to the next largest atom attached to that atom, which is going to be carbon for the group on the right and hydrogen for the group on the left. Therefore, the ethyl chain is 2, and the methyl group is going to be number 3. Now, when we should now draw a loop, and we see that it's going clockwise. And what I always do is I remember the way we draw the letter R. We draw the R, the first loop, we draw it like that, which is clockwise. The same thing happens here, where this is also clockwise, so this is going to be R. Now, the next molecule for the one in the middle is a little bit trickier because we only see there are only 3 groups attached to carbon. However, what happens is that organic chemists, when there's only 3 groups attached to a carbon and they're all single bonds, it is implied that the 4th group is actually a hydrogen. So because the methyl group is going into the plane of the page, that means the hydrogen is coming out at you. Now, our first rule is to always put the smallest group in the back. So because the smallest group is now in the front, we have to reverse our answer, whether it's R or S. So the first thing we do is we look at the largest group, the largest atom, which is O. The next is going to be a tie. We have 2 carbons. The next group attached to that is another carbon, or this is a hydrogen. Therefore, this is 2, and the methyl group is 3. Now, usually we would go like this and connect our lines, and we would see that that would also be R. However, since we have the hydrogen actually coming out of the plane of the page, we have to make that S. So therefore, the stereochemistry around that carbon is going to be S. Let's do the last example, the far right. Here we have a OH group coming out and 2 other carbon groups. Therefore, since there is no 4th group, that must mean that there's a hydrogen, and it must be going into the page. Therefore, we're all set. We don't have to do any reversal like we did for the second example. The largest atom attached would be the oxygen again. The second largest, we see it's going to be over here because we have a carbon attached to another carbon. And the third one is going to be the methyl group. So we go like that, and we see that's going to be S. Just like when you're drawing the letter S, you start by drawing it like this, counterclockwise. Same thing. Therefore, this must be S on the far right. Enantiomers. Enantiomers are non-superimposable mirror images of each other. That means that for the molecule on the left, you can put a mirror plane and draw a mirror image of the molecule on the right. And if you take these two and you were to try to move them around in free space and try to superimpose them on top of each other, they will not superimpose. For example, take your two hands, take your left and your right hand, and you will see that they are mirror images of each other, and you are not able to superimpose them on top of one each other. You'll see that your thumb and your pinky actually will be on the same side if you try to superimpose them. It just doesn't work. That means these are enantiomers, and that also means that these molecules are chiral to each other. So if we were to do the stereochemistry about the carbons, carbon, we would see that biggest group, OH, 2, 3, we do it around, this is going to be S, and therefore this one must be R, because if they are truly enantiomers, that means that the stereochemistry around every chiral carbon must be opposite. So if the one on the left is S, the one on the right must be R. We can check our work by putting a 1 on the OH, a 2 on the COH, a 3 on the methyl, goes around this way, and that would be R. So here's another example of enantiomers. The molecule on the left is R, and the molecule on the right is S, which from looking at them, we could assume that they are enantiomers. Now, in your mind, or if you have a molecule set, try to make this molecule, and if you flip it around, you will see that the wedge down here, actually when you flip it around, will turn into a hash, and that the alkene bonds actually also flip when you flip around the whole molecule. You flip it like that, you will see that they are mirror images of each other, and they are non-superimposable, meaning you cannot put them on top of each other, meaning basically that they are not the same molecule when you flip it around. So, interesting thing here, we have the molecule on the upper left has 2 stereogenic centers, both are R. Therefore, its enantiomer must have the exact same chemical structure, where the chirality must be S around both of them, because they must both be different. Therefore, they're enantiomers. So we see here, we have R, R, therefore its enantiomer would be S and S. If it were to be a diastereomer, on the other hand, we would have one of these being switched and not the other one. So if we look at the top diastereomer, we'll see that the top one is R and the bottom one is S. Obviously, if the molecule on the upper left were to also have a molecule that both had R and had the same structure, it's the same molecule. So oftentimes on an exam question, they might ask you to determine whether 2 molecules are either enantiomers, diastereomers, or the same molecule, and you have to be able to take the molecule in your mind and kind of flip it around and see if you could superimpose it and see if it has a mirror plane and all sorts of stuff like that. But it's always good to be able to determine immediately whether it's R or S, and that'll help you know whether it's an enantiomer or a diastereomer. Chair conformations, and it's in a separate topic. Chair conformations are 6-membered rings. They are mostly carbon, but can contain other elements like oxygen. In reality, we may draw these rings as flat, but in reality they aren't flat. They actually form a chair-like structure, such as we have this beach chair right here. It kind of forms a similar structure, and it shows the position of the side groups that are in space. So these chair conformations, we determine the positions of the side groups being axial or equatorial. Axial positions are going straight up or straight down from the ring, and those positions are very crowded to each other, and usually the smaller functional groups are going to be in the axial position when you're looking at one of these 6-membered rings. Whereas the equatorial we have here on the right in blue are going to be the more roomy positions. Larger groups are going to prefer these equatorial positions rather than the axial positions, and they are going to be always going at an angle when you draw them on your chair structure. So when we look at the chair conformations, these chairs are always going back and forth between the major conformation and the minor conformation. However, the major conformation is going to be the one on the left, because you'll see that the largest group on the left, the CH2OH, is equatorial. On top of that, we have OH, 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 also all being equatorial, which is much more favorable than these axial OH groups, and definitely more favorable in the axial CH2OH group. Newman projections. Newman projections allow us to look at a bond and see the different interactions between the side groups. So oftentimes you may be given what they call a sawhorse projection, which is going to be written like this on the left over here. But this is kind of difficult to tell how the interactions between the different groups are working. So oftentimes they draw a Newman projection, which is shown on the right. So Newman projections, to be simple, are you're looking down the plane, you're looking down this line right here, down the bond, and you're trying to understand how the side groups are interacting with each other. So to make it easier, I drew this blue circle, this blue disk, and this blue disk is in the middle of a bond. It's not on a carbon, it's in the middle of a bond. There's a single bond going between the carbon here and the carbon here, and there's a blue disk just smack right in between them. And you'll see on the figure on the right in the Newman projection, you'll see that there are three groups, the CH3 group going straight up, and the two hydrogen groups that are going downwards at an angles, and those groups all have a black line going from the center of the blue circle out. Those three groups correspond to these groups here. Those are in front of the blue circle. The three groups behind the blue circle, which are going to be over here, correspond to the groups in the back, because those are behind the circle. So that's the basis of a Newman projection. Now, there are different types of Newman projections. There are staggered Newman projections, and all these are staggered. And what staggered means is that the molecules are not right on top of each other. The groups, rather, are not right on top of each other. And these staggered conformations can be categorized as anti or gauche. And we'll see on the left that the two largest groups, the bromines, are opposite each other, therefore they are anti, whereas the gauche interactions, the BRs, are adjacent to each other, so they are gauche. All three of these are staggered because, like I said, they are not right on top of each other. The eclipse conformations, on the other hand, are the side groups directly overlap. So we have a hydrogen and the methyl group here that are right on top of each other, and these cause for elevated energies because it's not very happy with these big groups being right by each other, or these groups being right on top of each other. And eclipse conformations do not have a different name based on whether the largest groups are on top of each other, whereas we have the staggered, we had anti and gauche, which are both staggered. Eclipse is usually just called eclipse, or at least that's what we learned in 512. The different energy levels of the Newman projections, we see that all four of the staggered conformations, we have these four, they are all lower in energy than the eclipse conformations which we have above. And you can see that there is one conformation, the one in the middle, which has the highest energy, higher energy than the other two eclipsed, and that is where you have the two large groups, the two CH3 groups directly on top of each other, and that is going to be the highest energy Newman projection. So this is a good pattern to know and understand why certain molecules are at higher energy than others. So that is the end of part 2 for exam 1 material. Next video will be the final video for exam 1, and after that I'm going to be making a review problems that I'm going to go over for exam 1 that will be going directly over problems from past year's exams. Thank you for watching and hope to see you next time.